Okay, good morning, everyone. Very happy to have this third talk this morning by Lyne Moser from the University of Regensburg, who's going to tell us about model structures for double categories. Lyne, please.
Yeah, thank you very much for the introduction and also for the invitation. I'm glad we made it work. So yeah, as you said, today I will speak about model structure for double categories. So like studying the homotopy theory of double categories. And before giving you some motivation for this, I just want to recall what are double categories. And so let me start by telling something about two-dimensional categories. So we have two different types of two-dimensional category, and the first thing you could do is like enriching in categories, and this is what's called a two-category. So a two-category is just by definition an enriched category in categories, the category of categories. And what do I mean by this? So I have objects like in a category, but then I also have my morphisms, but now my morphisms, they're enriched in categories, so they themselves form a category. So now I have a category of morphism, and that means that I further have a further notion of morphisms between my morphisms, which I call two morphisms. And so we can depict them like this. And typically, the canonical example of the two categories, the category of categories themselves, because I can take as objects my categories, and then as my morphisms the functors, and two morphisms the natural transformations. Okay, and then we have a second type of two-dimensional category, which are the double categories. And this time, instead of enriching over cat, I will internalize into categories. So a double category is by definition an internal category, two categories. And so by this now, I mean that I have both a category of objects and a category of morphisms. So first I have, as I said, category of objects. So I have my objects, and then I have some sort of morphisms between them, which I will call vertical morphisms, and depict them like this. And so this is what I would call my category of objects. But then, as I say, I also have a category of morphisms. So I have a second type of morphisms between my objects, which I will call horizontal morphisms, and depict them like this. And then I have this, so this also is a category. And then the morphism in this category, they both have two horizontal boundaries as well as two vertical boundaries. And so they are called squares, and they look like that. Okay. And so, of course, I have a bunch of compositions for all these structures, which are associative and so on. And what I can notice too is that if I look at the two category, it can be seen as a double category where my vertical morphisms are all trivial. So every two category is a double category with all vertical morphisms trivial. And so I would have objects, then just identities here. Here I would put all of my morphisms, and then my squares, they would have, they would look like this, because vertically I can only put identities, and so I can just pick them to be my two cells again. And so this is actually a functor from the category of two categories and two functors to the category of double categories, which is sometimes called the horizontal embedding. Okay. So that's just for a quick introduction to what two categories and double categories are. And now I would like to give a motivation for this double category. So why do we care about them? And I'm going to give you my motivation, and I know that there are probably other ones too, for example, in monad theory and so on. And so my motivation for studying this double category was coming from the motivation to study two-category theory itself. And so study two-category theory. And two-category theory is a very important part of category theory too, just starting from the fact that category themselves form a two-category, right? Okay, so why does it have studying two-category theory? So in ordinary category, a classical theorem says that the following, namely that limits of a functor f can be characterized as the terminal objects in the category of cones over f. So these are the same thing as terminal objects in the category of cones over f. And so now you could ask yourself, okay, what happens if we look at two limits, so like limit of a two functor instead, and these are called two limits. And instead of having a universal property expressed in terms of an isomorphism of sets, it's expressed in terms of an isomorphism of categories now. And so you can ask yourself, what happens if I just put two everywhere and ask myself, does the two limit, is the two limit the same thing as the two terminal object in the two category of codes? And this is actually not true. And this is with slick Riemann, we provided very small counterexamples, which shows that this theorem just fails in general. And so what Grandis and Parry suggested instead is to pass to a double categorical setting. And there you can formulate such a theorem. And namely, you can say that two limits correspond to double terminal objects in the double category of cones.
What is it to limit? I mean, I think I might understand what limits of the two functions, but what is the two limit?
So like, you know, like for a limit, you have a universal property like this. It's the same as the functor. Like the cones over f are the same as the maps into the limit. And like actually when you're in a two category, now this is a category, and this can be structured as a category as well. And so actually, instead of asking for an isomorphism of sets, now you ask for an isomorphism of categories. So like it has extra structure because now you have two different universal property, one on objects and one on morphisms. Yeah. Thanks. Okay, so this I was saying is Grandis and Parry. And in fact, this is not specific to two limits, like it's actually about like any representable functor. And we also have this result with Marusa Razola and Paolo Verdugo in a much more general case where you can actually take enriched categories on one side and internal categories on the other side. But now, because this talk is about homotopy theory, I just want to mention that there's also a notion of bi limits of two functors, where by limits, I mean that this is now not an isomorphism of sets anymore, but instead it's an equivalence of category, right?
Sorry, Lynn.
Yes.
That might not be so visible.
Okay.
Perhaps another color. Yeah.
Yes. So now we ask this to be an equivalence of category. And again, the same counterexamples that we have, they show that even if we are in the more homotopical context, these two are not going to be the same. And instead, we come up with a notion of double biterminal objects, which capture this notion of band limits. And this we did again with Klingman. So what we see is that double categories are very convenient to re-express certain universal properties of two categories. And in fact, because we have these homotopical notions of limits too, we would like to have an abstract framework given by the homotopy theory of double categories to be able to express this maybe in a more abstract way. And so the goal of this talk is going to be to provide a homotopy theory of double categories that is compatible with that of two categories. Okay. So the language I use to do homotopy theory is that of model category. And maybe I want to recall quickly what these are. So
it's also fading. Maybe we can use blue.
yes, so yeah, that's much better.
Thank you.
So model categories are a nice structure to do homotopy theory. And so a model category is going to consist of bi-complete category, first of all. So by complete, I mean both complete and co-complete. And then we will specify also 3 different classes of morphisms in the category. So 3 different classes of morphisms in M. And so the first one is the class which we will denote W, and it's the class of weak equivalences. And so these are like the main player of a model structure because they tell us how to identify objects up to a homotopical notion of isomorphism. So for example, you can think of these as the weak homotopy equivalences between spaces, or as the quasi-isomorphism between chain complexes, or these kind of things. And this formalizes these kind of structures. And then we also have the co-fibrations and the fibrations. And these are more like a technical addition to a model category. So they are more like there to make things work and to allow us to make computations such as derived Fokker or homotopy limits and co-limits. And so all of these, they satisfy a certain axiom, which can be summarized as follows. So W satisfies 2 out of 3. So, and then the class of co-fibrations is also weak equivalencies and fibrations, as well as the class of co-fibration and the class of fibrations that are also weak equivalencies from weak factorization systems. So it's not very important if you don't know all of what this means, because I'm not really going to use them throughout the talk. But the important thing is that this class determines the order because of this weak factorization system. And so in particular, to give the full data of a model structure, once we know it exists, it's enough to just give the class of weak occurrences and one of these 4 classes. So like model structure is determined by, let's say, weak equivalencies and fibrations, or weak equivalencies and trivial fibrations, and so on. Yeah, also this I didn't say. I will call the co-fibrations that are weak equivalencies trivial co-fibrations, and the weak equivalencies that are also fibrations trivial fibrations. Okay. And so in a model category, there are specific subclasses of objects that play a very important role, and these are the fibrant and the co-fibrant objects. Is that too long? No.
That's okay.
Do you still see? No. Maybe I keep going up here. Quickly. So an object X in my model category is fibrant if the unique map to the terminal object is a fibration. And then it is co-fibrant if the unique map from the initial object is co-fibration. And these are well-behaved objects because usually when you look at the weak equivalencies between these objects that are both fibrant and co-fibrant, then there are really these maps which have an inverse up to homotopy or something like this. And so another theorem by Joyard tells us that actually it's enough to give the fibrant objects and the co-fibrations to determine the full data of the model structure. And so equivalently, the fibrant objects and the trivial co-fibrations, because co-fibration and trivial co-fibration determine each other. Okay, any maybe question? This was a bit fast, but I hope it will help understand a bit what's going on in the rest of the talk. Okay. So before going to double categories, let me recall the model structure for two categories. So there is a canonical one. And so I will start by telling you what the weak equivalences in this model structure are. And so maybe you can remind yourself that a functor between categories is an equivalence if it is subjective on objects up to isomorphism and then fully faithful on morphisms. And so we're gonna weaken distortion for like two functors instead. So a two functor is a bi-equivalence if the following happens. So the first thing is that it is subjective on objects up to equivalence, and I'm going to explain in a bit what I mean by an equivalence, but it's like a weakened notion of like an isomorphism. Okay, maybe I can do this now. So an equivalence in a two category is a morphism such that it has an inverse. But now, because we have a notion of two morphisms in a two category, we can just ask that the composition of these inverses are just isomorphic to the identity. So, and two isos, by two isos, I mean two morphisms, which are isomorphisms between the identity and the composites. Okay. So this resembles this idea that it's subjective on objects up to some kind of invertible morphism. And then we will ask it to be full on morphisms up to two isomorphisms. And then fully faithful on two morphisms. And so these last two conditions kind of tell you that a two functor is locally an equivalence of categories. So like it uses an equivalence between the categories of morphisms. Okay, and then the theorem by Steve Lack, says that there is a model structure on two categories where exactly those weak equivalences. So the weak equivalences are the bi-equivalences, and then the trivial fibrations are the two functors which are subjective on everything. So two functors that are subjective on objects and then full on morphisms and fully faithful on two morphisms. Okay.
Just ask by two categories here with me strict ones, so does it matter for you?
I mean strict ones, but I think like also has this model structure on bi-categories, but somehow it has to take like strict functors between bi-categories, which is not very natural. but yeah. And then like the two model structure are equivalent equivalent. And this is like another instance of bicategories can be strictified to true categories.
But so what you're going to do, everything is almost strict to category.
Yes, yes. Okay, so one consequence of like the trivial fibrations being these two functors, we can really identify the cofibrant objects. So the cofibrant two categories are those such that the underlying category, so like the category I obtained by just forgetting about my two morphism, is free. So by free, I mean I take the graph and then like all compositions are free and so on. And so one cofibrant replacement that we can find actually comes from the theory of normal pseudo functors between two categories. So if I look at my category of two categories and two functors, I can include it into the category of two category and normal pseudo functors, where here like functoriality of the functor is only up to isomorphism. And this has a left adjoint, let's call it Q. And this left adjoint acts non-trivially on objects. So like it really takes a two category and forms another two category. And actually Lack shows that this unit map that you obtain from the adjoint is a cofibrant replacement. And so by this, I mean that this guy is cofibrant, so its underlying category is free, and this map is a bioequivalence. And in particular, this QA is the normal pseudo classifier of the two category A. And by this, I mean that because of this adjunction, if I take a normal pseudo functors from A to B, then this corresponds to a strict functor from QA to B. And so somehow we can think that like this cofibrant two categories kind of allow us to talk about pseudo functors in this theory too. And another fact about this model structure is that all two categories are fibrant. It's getting bad.
You could use this. Sorry.
Yes. I'm gonna kill them.
You get back to you. You get back to you.
Ah,
Yeah.
That will show.
and then it's
Keep
refilled.
pressing and writing what you do.
Okay, okay.
It lasts a little longer.
Yeah, thanks.
But maybe that one is new. Either way.
Let's see. And so then we can formulate a weighted theorem. Okay, maybe I'll just a weighted theorem which says the following. So as I was saying, between cofibrant fibrant objects, the weak equivalencies have an inverse up to homotopy, but like because of these facts, actually you can find an inverse for any two functor. So two functor f from A to B is by equivalence if and only if there is a normal pseudo functor the other way around and two pseudo-natural equivalences between the identity and the components. And it's not very important if you don't know what I mean by pseudo-natural equivalencies, but one point that I want to make is that they actually corresponds to the homotopies in the model structure. So this is really saying that for any by equivalence, I can find a weaker notion of an inverse, which is related via homotopies to my which relates the composites to the identities. Okay. So that's what for the canonical model structure on two categories. And now we are going to pass to double categories and try to do similar things. Okay, so as I mentioned before during the motivation section, the goal is to find a homotopy theory for double categories, which contains that of two categories. So we want to find a model structure on double cats such that this horizontal embedding is homotopically well behaved. And so just like one note about like what had been done previously for model structure on double categories. So previously there were several model structure on double categories by Fiore, Frank, and Pauli. But like they induced it more like from one category, so, you know, instead of like inducing them from two categories. So like they didn't really see the two category aspects of double categories. And so that's what we did then in our work, like trying to make this more two categorical. And so to build such a model structure, what we used is a classical theorem, which tells you how to induce a model structure from an adjunction. And let me record this. So if we have an adjunction from a category to a model category, so here I have the full model structure, where here it's the right adjunct, left adjunct. So if we have such an adjunction and we have some assumptions, so one of them is taking care of the size issues, then another one is asking for fibrant replacements, and the last one for path objects. So size, fibrant replacement, and path objects. I don't want to be very precise about these, but like there are few assumptions that are checkable. And then under this assumption, then the right induced model structure on N exists. And in this right induced model structure, we have that the weak equivalencies, the induced weak equivalencies along the right adjoint. So they are just the pre-image of the weak equivalencies in M. And the fibrations are also the pre-image of the fibration. And in particular, because the trivial fibrations are the intersection of the fibrations and the weak equivalencies, we see that the trivial fibrations are also the pre-image of the trivial fibrations.
So I got lost at some point. I'm sorry, you probably said this, but there's a theorem that you raised. There's someone black people on
two categories.
Two categories.
Yes. So we have already a model structure here, and now we want to put one here, which is compatible with the one we saw before.
Because I'm not sure what you guys have done. This purely function.
So they put a bunch of model structure on here.
They put what?
They put several model structures on double categories,
Okay.
but they were not compatible with this embedding. Like
you have a new one.
Yeah, exactly. We build one that is more two categorical in flavor. Yeah. Okay. So the first question is like, what kind of adjunction do we want to consider? And so first, the horizontal embedding has a right adjoint. And this right adjoint takes a, sorry, pointing the wrong way. And this right adjoint takes a double category to its underlying horizontal category. And so here objects are just the objects of the double category started with, and the morphisms are the horizontal morphisms, and the two morphisms are just the square which have trivial vertical boundaries. So basically we forgot all the vertical structure of the double category. But this, if we induced it along this adjunction, it would not be great because, like, as I said, we don't see the vertical morphisms at all anymore. And so what we can do is like add a shift. So we can include and then product with the vertical morphism. So this is just the double category free on a vertical morphism. And so this gives us another functor like this, and it has a right adjoint because double categories is Cartesian closed. And so assembling these two together, because we have two source and target maps, form an adjunctions between double categories and diagrams of the following shape in two categories. And I'm probably gonna get this one. Okay. So where I have the two source and target map and identity map. So this would be H, V2 blank.
Sorry, second, what is the right adjoint? H of V2 with some.
So this is the internal home in double categories.
From what same case? What is V2?
V2 is the vertical morphism. So it's just like the
Oh,
double
it's a
category
free-
which has just one vertical morphism. Yeah. So it's like which shifting this construction like 1 degree up, and like what happens now is that we have a category whose objects are the vertical morphism in A, and then the morphisms are the squares in A, and now we see all squares, and the two morphisms are something that I don't want to read this too, but yeah. So now we capture most of the structure of the double category, and so what we showed then with Marusara Zola and Paula Verdugo is that the right-induced model structure on double cat along this adjunction, where here I can put the projective model structure. So from the projective model structure on 2cat. And so the projective model structure is defined on functor categories, and here the weak equivalencies and fibrations are defined level-wise. So I just evaluated 0 and 1. I test whether it's a fibration or weak equivalencies in two categories, and then this defines my model structure. So the ranking from the projective model structure on double cat exists. And so this gives us a first model structure. So let's try to study it a bit.
Sorry, what was the reason for introducing this interval? What about the first adjunction? Did that transfer exist?
Yes.
No, I mean, okay, the second, this one, yeah.
Yes.
Oh, and now it's the third.
Yeah, and actually the transfer here and the transfer here, like they coincide, but I'm doing this on purpose because later I will use it again. Yeah. So it would be enough to just transfer along this one and you would get the same result. But this is because we transfer from projective. Okay. So what are the weak equivalencies in this model structure? So we have an explicit description because they're just the double functors such that evaluating both this functor and this functor, they lead by equivalencies of two categories. but we can find a more explicit description of them, which resemble a bit the one that we had before. And so they are the double bioequivalences, or horizontal double bioequivalences, if you want. And so these are the functors that are surjective on objects up to horizontal equivalence. And by horizontal equivalence, I just mean an equivalence in the underlying horizontal 2 category, surjective on vertical morphism up to invertible square, and then full on horizontal morphism up to invertible square, and fully faithful on squares. So they resemble the equivalences that we had before. And then if we look at the trivial fibration instead, we get something similar, so surjective on objects, but then we only get surjective on vertical morphism, which is different than full because you're not fixing the end objects that you're looking at, and then full on horizontal morphism and fully faithful on squares. And so this is like, as I say, this is not great because surjective is not the same thing as full. And then this will make the cofibrant objects not very well behaved, because here the cofibrant double categories, they are those double categories such that the underlying horizontal category is free. So like this is good. So underlying horizontal category is free. And by this, I mean the category of objects and horizontal morphisms. But now the underlying vertical category cannot have any composable morphisms. And by this, I mean non-trivial. So like you can still compose identities with morphisms, but you cannot have two non-identity morphisms that you can compose. And this is kind of disappointing because we would like something such as both horizontal and vertical categories are free, so that then we can have some kind of normal pseudo-functor classifier also for double categories.
You have factorization. That come with the data of categories.
Yes.
So you do have it.
Yeah. Like as soon as I say the model structure exists, I have all the factorizations and yeah. And then another thing that's true also in this model structure is that all double categories are fibrant. And this is actually not great because we cannot formulate a Whitehead theorem here with all double categories being fibrant. And this was already something that Grandis noticed by just looking at the level-wise equivalences of categories. But the nice thing that was our goal, though, is that the functor H is well behaved homotopically, and actually it's both left and right Lyne. Left and right Lyne embedding. And by this, I really just mean that I have two model structure and I have a nice way of comparing them. Yes. Okay. So as I said, there are a bunch of problems with this model structure because the cofibrant objects are not very nice. Maybe we want to restrict a little bit on the fibrant objects, and so we instead built another model structure that fixes these issues. When did I start?
You have probably 10 more minutes. Is that okay?
Yeah, okay. Okay, so second model structure on the book. And so the idea to fix these problems is like try to use the same adjunction that we had before, but instead change the model structure that we are inducing from. So if you remember, we had two categories with this functor category. And now we would like to ask ourselves, okay, let's not take the projective model structure, but instead another model structure. And the nice thing is that this has a ready model structure, which comes from like a truncation of delta, or like it's very easy to see in this case. And so we do have a ready model structure on this functor category. And so what we would try to do is instead try to write induce from this model structure. And so here the weak occurrences are again level-wise, but then the cofibration and fibration are a bit more complicated. Okay, but the problem is that this doesn't exist actually. This right-induced model structure doesn't exist. Okay. And so what we did then was like come up with a general theory that we could apply to this specific case. And we modified a little bit the notion of right-induced model structure by making it less strict. And so this is something we did with David, with Leonard Guetta, Maru Sarrazin, and Paul Verdugo. And we showed that given an adjunction as before, between n and a certain model structure, then and some assumptions. And so again, we have some size issues requirement, the path object as before, but then the fibrant replacement becomes automatic with this model structure, and instead we need to check that trivial fibrations are weak equivalences. And so under this hypothesis, we can show that the what we call fibrantly induced model structure on N exists. Where like by fibrantly induced model structure, so as I was telling you at the beginning, it's enough to precise the fibrant objects and the trivial fibrations. So I'm gonna choose my fibrant objects to be the pre-image of the fibrant objects, and the weak occurrences, the trivial fibration, sorry, to be the pre-image of the trivial fibration. And now the weak occurrences, they are not determined by the pre-image of the weak occurrences anymore, but like you can still show that they are still the pre-image of the weak occurrences between fibrant objects. So weak occurrences between fibrant objects are the pre-images of the weak occurrences. So this gives another homotopy theory, which between fibrant objects is still the same one as before. So it kind of models the same idea as the right-induced model structure. But as we see in this case, while the right-induced model structure does not exist, the fibrantly one will exist. Okay, so the fibrantly induced model structure on double categories from the same adjunction as before, from the ready model structure on 2cat exist. And so in particular, by doing this, we fixed our problem with the trivial fibrations, because now trivial fibrations, they are just the subjective on objects, full on horizontal and vertical morphisms. and fully faithful on squares. And so this tells us that the cofibrants double categories are now better behaved, and they are given by those such that the underlying horizontal and vertical categories are free. And so in particular, one cofibrant replacement would be given by, again, looking at this normal pseudo-functor classifier. So for double categories, we also have a notion of normal pseudo-functors, which preserve all composition up to isomorphism. Then this will have an F-touchlines. And so this would give you a cofibrant replacement. Maybe I'll just say the name of the fibrant objects and give just like the White theorem, and then I'll be done. So the fibrant objects in here, they are what we call the weakly horizontally invariant double categories. And this terminology comes from Grandis, where he had horizontally invariant double categories, and basically a notion is just a weakening of this notion. And so the weakly horizontally invariant double categories, if you know what I mean in the next sentence, you can take it. If you don't, you can take it as a black box. But they are such that all horizontal equivalences in the double category have companions. Yeah, maybe I don't want to get into the details of what this means. But basically it implies that two objects in my double category, they are horizontally equivalent. If they are horizontally equivalent, then they're also vertically equivalent. And this is something that's very useful then to formulate a Whited theorem. And so the Whited theorem says that the double functor between A and B is and I want A and B to be weakly horizontally invariant. So is a weak occurrence. So first of all, because of this general theory, I know this happens if and only if it is a double bioccurrence. And this happens if and only if I have a normal pseudo functor, which is its inverse up to homotopy. So normal pseudo double functor G from B to A. And to horizontal pseudo-natural equivalences, which again are just my homotopies in my model structure. Okay, but then our main goal was to have a homotopy theory which retrieves that of two categories. And so again, we will ask ourselves, is the horizontal embedding a Quillen embedding? And it happens to be a left Quillen embedding, but not a right Quillen embedding. But it's okay because we can just do a slight modification where like the vertical morphisms are given by the equivalences instead of the identity, and this works. So we have that this one is left Quillen embedding. And then we have that a slight modification of it, as I say, where I take the vertical morphisms to be the equivalences rather than just the identities, and up to homotopy, this doesn't change anything to the construction, is right equivalent embedding. And in particular, the two, they are double by equivalent. So really, like, they're just the same construction at the homotypical level. And yeah, maybe also. Yeah. Thank you very much for your attention.
Questions for Lyne?
Something about the theory with the pattern objects and alarms that correctly are sort of vertically with frequencies in one direction. So it's like a two category, but instead of identifying the objects, it's with frequencies.
Yeah, it looks more like this.
Okay, perfect.
But like, you know, up to homotopy, I can contract all my equivalences and then you just the same thing as the two morphisms. Yeah.
Okay. And so one difficulty that comes up in doing category theory, just like in general, is that you always have a central object instead of like, you know, a group load of objects. And if you work instead with a group load of objects, you can just do double categories. Complete single object in one direction, complete single object in another direction, and the correct notion of equivalence becomes just like level-wise equivalence.
Yes.
Okay. So what I'm wondering is, can you model double infinity categories in the sense where in both directions they're just secretly one categories by that kind of double category? Do you know what I mean?
So I don't know if this is gonna answer the question, but there's like so in my thesis I write a nerve inclusion from double categories to double infinity categories.
Okay.
Which is gonna preserve and reflect weak equivalences between finite objects. So
okay.
And this condition is kind of like, and like if you study it a little bit, you will see that this condition is very necessary to have the 3D vibrancy at the infinity level as well.
Okay.
Yeah.
And you get no, I think this answers my question. And the image of this conclusion, is it really like just is the image what it's supposed to be, which is what I said before. We have like category objects in both directions.
Yeah.
Okay.
But like I think actually I would look more at them as like, you know, simplicial object in two categories here, because like you're reading this to just make sense of equivalences, which you don't if like you're just looking at one category, like strict one category. Yeah.
Okay.
Good. Any other questions? Okay, if not, let's thank Lyne again for the very nice talk. Thanks again.